Now listen. Then in the beginning again, I'm going back to electric flux. Remember, now we can divide electric fluxes into two different stories. One is going to be effective electric flux. Other one is going to be standard electric flux. Mainly we are dealing with effective electric flux only. Remember, effective electric flux means perpendicular intensity into the intensity perpendicular to area into the area. If not, the charge over the permittivity. These two represent effective electric flux. What is standard electric flux? Standard electric flux equals to just Q, sigma Q, just Q. If not, standard electric flux is going to be intensity perpendicular to the area into the area into the permittivity. Right? That's the difference. Okay, in a summary, I will give that idea. Right. Now let's see what they are telling in the Gaussian story, what they are telling. In Gaussian story, what they are telling. Right. Right. Now put your topic. Finding the intensity around charge distribution using Gaussian theory. Subtopic. Finding the intensity around charge distribution using Gaussian theory. Finding the intensity around charge distribution using Gaussian theory. Now, what is this charge distribution? What is charge distribution? Write down below. Subtopic, charge distribution. Subtopic, charge distribution. Number one. Sorry, no, write down. Under charge distribution, write down. There are three types of charge distributions. There are three types of charge distributions. There are three types of charge distributions. Number one, write down. Linear charge distribution. Number one, linear charge distribution. Linear. Number two, area charge distribution. Number two, area charge distribution. Third one, volume charge distribution. Third one, volume charge distribution. Right? Okay. Still you are not that much of familiar what is this charge distribution. Still you have no idea. Don't worry, you will understand now. Right? Can you remember density? When I was teaching about hydrostatics, when it comes to density, we were talking about linear density, area density, and volume density. Just can you revise back and can you please tell me what is linear, area, volume density? Volume density. If when I was teaching about this elasticity section, I was teaching about deformation, 1D, linear deformation, area deformation, volume deformation. I explained that linear in the sense mainly that is for a object having a length. But we know in the universe, all the objects are three-dimensional objects. Even you consider our hair, a girl's hair. Even that hair is also having a kind of volume. Yeah, it has a larger length. It looks like it has only length, but when you consider even the hair, that hair also having a volume. It is having a length, width, diameter. Right. So when you consider any object in the universe, they are three-dimensional. They have a kind of volume. But what we do, we consider if an object's length is considerably higher than other dimensions. The best example is a girl's hair. Then we define linear density. But it means linear. Area means if an object's area is significant, considerably larger, if its area is considerably larger, then that is we are considering as area density. When I was teaching about density, volume density means if an object is having a volume, then it's a volume density. Likewise, when you consider charge distribution also, a charge distribution means what simply? So what is charge distribution? Charge distribution means just think positive and negative charges, right? Just consider protons and electrons. Just think like that. Just think protons and electrons. Depends on how these charges concentrated, how the charges distributed in a certain object. Depends on how these charges distribute, if not spread on a certain, if not spread in a certain, spread on a certain object. What we can do, we can define them into different charge distributions. Now, linear charge distribution, area charge distribution, other one is volume charge distribution. Now, by the name you understand. So you are telling charge distribution means how the charges have spread on a certain object. So if it is linear charge distribution means you are coming to tell these positive negative charges have spread along a lengthy object. Is that what you are coming to tell? Yes. If it is area distribution, so the charges, maybe positive or negative charges, have spread along a area of an object. Right? Volume distribution means the charges have distributed inside a whole volume of that object. That you can get the kind of idea. When you draw the diagrams and all, you will understand more. Right? So you have an idea about what is charge distribution roughly. Then we define the three categories: linear, area, volume charge distributions. That is also done. Now we'll go to next story. Next story, write down. Next story. Next story, write down. Next story. We'll talk about what is this linear charged. Okay, under, write down. Under linear charge distribution, put your subtopic linear charge distribution, subtopic linear charge density. Linear charge distribution subtopic linear charge density, another subtopic, write down. Linear charge distribution subtopic, another subtopic is linear charge density. Linear charge density. Charge density. There's a symbol for this. That is lambda. Symbol is lambda. Lambda. Now, can you remember what is that linear density? Not charge density. Can you remember what is linear density? If you can remember, linear density means I told you that mass per unit length. Normally, the symbol of linear density is simple M, if you can remember. Mass per unit length is we defined as linear density. Can you remember when you consider an object having a length, considerable length? If the length of an object is significant than other dimensions, let's say the total mass of this object is capital M and the total length of this object is simple L. Linear density means 1 unit length, 1 meter length, what is the mass? When you consider entire simple L length, mass is capital M. When you consider 1 meter length, a unit length, what is the mass? That is what we defined as linear density. Same story. Then what should be this linear charge density? When you consider an object having a length significant than other dimensions, right? Just consider as an object, that object's length is significant, considerably larger than other dimensions. Maybe a kind of very thin, larger lengthy rod, larger conductive lengthy rod. Okay. Just something like that. And you notice that charges are distributed on this lengthy object in this manner. The charges have spread along this, on this linear object in this manner. Charge distribution is kind of linear charge distribution. Right. The length of this object is, let's say, simple L. The length is simple L. And the simple L. Length is simple L. And when you measure the total number of charge along this simple L length, if you measure the entire charges on this length, the total charge accumulated, the total charge spread on this length is, let's say, capital Q. Capital Q. Capital Q. Then how do we define the linear charge density? We can define, so for simple L length, the total charge on simple L length is capital Q. So then for 1 meter length, for a unit length, what is the charge distribution? 5 chocolates, 10 rupees. One chocolate, how much? 5 chocolate, 10 rupees. One chocolate, how much? How do you find? You divide 10 by 5. Then only you get one chocolate price. It's 2 rupees. Likewise, for simple length charge is Q. For 1 meter length, for unit length, what is the charge? Capital Q over L. That is what we defined as Q over L. Unit length charge. That is what we defined as linear charge density lambda. Lambda. Right? So you guys draw this diagram and write the story. Then we can write down linear charge density means total charge over total length. We write an equation. Linear charge density means total charge over total length. You can write it down. Linear charge density. Charge density means total charge over total length equals total charge over total length. Total charge over total length. If you go with symbolic method, symbol, lambda going to be equal to Q over simple length. Q over simple length. And the Q over simple length. And highlight this equation, these both equations. Highlight. Shall we find the units of linear charge density? The units. The units. Then we all know that charge measured in coulombs, capital C, length measured in meters, simple limb. The units of linear charge density is going to be coulombs per meter. Coulombs per meter. Story. Write down. Story write down. Story write down. Finish writing answer. If you finished writing, raise your hands. Okay. Right. Sample question, write down. Sample question. Write down the sample question. The linear charge density of metal varies. The linear charge density of metal varies 20 millicoulomb per meter. 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 If you are hearing an issue, tell me. 20 millicoulomb. 20 millicoulomb per meter. 20. Are you facing an issue? Tell me. 20 millicoulomb per meter. Just hands up. How many of you facing any issues? You are facing any issues? Just raise your hands if you are facing issues. No issues at all. Raise your hands. No issues. Right. Then, okay, now question. Full stop. What is the total charge along the wire? What is the total charge along the wire if the length is 50 centimeter? If the length is 50 centimeter, what is the total charge? What is the total charge along the wire if the length is 50 centimeter? Find the answer. Very simple substitution. Length is 50 centimeter. Find the total charge acting on this wire. It is 50. Find the answer. Then we know that they are asking the total charge. They have given the linear charge density is lambda. Length is given. Then we know the equation. Lambda going to be equal to Q over simple L. Then I want to find Q. Then Q must be equal to lambda into L. Q must be equal to lambda into L. My lambda value is how much? Lambda is 20 millicoulomb. How do you convert millicoulomb into coulombs? Multiply by 10 to the power minus 3. Then you will get millicoulomb into coulombs per meter into the length. Length is 50 centimeters. How do you convert centimeters into meters? If you want to convert centimeters into meters, multiply by 10 to the power minus 2. Multiply by 10 to the power minus 2. When you simplify this, you will get the answer. You will get the answer. Then put a subtopic area density. Then put a subtopic under area density. You can define area charge density. We can define area charge density. Okay, if you directly put the subtopic as area charge density. Area charge density. Next subtopic is area charge density. This one answer going to be 10 and these two cancel out. Here 10 and 10 to the power minus 2 coulombs, right? If I'm correct. Then put a subtopic area charge density. Write down. Write down that story. Write down. The definition, write down. Definition. The charge, write down the charge per unit area. The charge per unit area is defined as area charge density. The charge per unit area. The charge per unit area is defined as area charge density. Then follow the same story. Area charge density. The symbol is area charge density symbol is sigma. Symbol is sigma. So in this scenario, now this charge distribution has happened along an area. Along an area, charge distribution, uniform charge distribution has happened. Right? So you can consider an area. Okay, it can be an area. This area is capital A area. When you consider surface area, just consider whiteboard surface. Along this whiteboard surface, a charge distribution has what? A charge has distributed along this whiteboard surface area. It's going to be a kind of area charge distribution. Correct me? Along this whiteboard surface, like my ink marks, like the ink marks, how these ink marks have spread along this whiteboard. Similar manner, think these ink marks as charges, positive charges, negative charges, things like that. How the way these ink marks are spread in the whiteboard, similar manner only charges distribute on this whiteboard area. This is going to be kind of what? It's going to be kind of area charge distribution. area charge density means same story. When you consider capital A area, the total charge on this capital A area, let's say that is capital Q. Area is capital A, the total charge is capital Q. Then you can tell for capital A area, the total charge is capital Q. When you consider 1 unit area, 1 meter squared area, what is charge? That is going to be the area charge density. Capital Q over A going to be our area charge density. That is sigma. Sigma. Just write in the equation. I'm not writing the equation. You write in the equation. Area charge density equals total charge over total area. Total area. Write the equation. The next step, sigma equals capital Q over capital E. Write that quickly. Write down the equation. Definitely after writing these stories up to here, write the equation. Area charge density equals total charge over total area. Total area. There are this equation. Then this Q going to be, the units of Q going to be coulombs. Area means meter square. Then the units of area charge density going to be coulombs per meter square. Coulombs per meter square. Story done. Now can understand what I'm going to do. The next topic is volume charge density. Next topic going to be volume charge density. Next topic going to be volume charge density. Before doing before going for the volume charge density, we'll do a small sample question. Hands up, finish writing hands up. Finish writing, raise your hands. Finish writing, raise your hands. Finish writing. Then Then write on a sample question. The total charge along a 5 meter squared area is 50 coulombs. The total charge along a 5 meter squared area is 50 coulombs. Problem number 1, find the area charge density, find sigma. Problem number 2, find the charge in 2 meter squared area. Find charge in 2 meter squared area. Find that. It's not difficult. Sample question SQ. They have given the total charge. Total charge given us how much Q is, we all know Q is how much, 50 coulombs. The total area given us how much, 5 meters square, 50 coulombs. The total area capital is going to be 5 meters square area. If I want to find the, under Roman number 1, if I want to find the area charge density, where is the equation? Sigma equals Q over E. So we all know that sigma equals Q over E. The sigma equals, we all know that capital Q over capital Q over capital E. Q over capital E. Then we can substitute. Now Q is going to be 50. Q is 50. Capital A is going to be 5. Then we can take the 10 coulombs per meter squared. That is one story. Roman number 2, they are asking that what is the, then now you know the area charge density, you know that. Then they are asking us to find the total charge on 2 meter squared area. We know that when you consider 5 meter squared of area, charge is 50. If it is 2 meter squared of area, the charge is going to be, no need to do the calculation, it's going to be 20 coulombs, right? 5 meter squared area charge is 50 coulombs. When you consider 2 meter squared surface, the charge is going to be 20 coulombs. That is one way. You can directly tell. If not what you want, you can substitute to this equation again. You can substitute to this equation again. Roman number 2. If you substitute this equation again, just now you found the area charge density sigma. If you substitute, sigma equals capital Q over A, sigma going to be 10 coulombs per meter squared, right? Then when the area is 2 meters squared, we want to find the total charge. Let's say I say Q. Then again Q is how much? Q is going to be 20 coulombs. Same story. Then the last one, put a subtopic volume charge density. Volume charge density. Next topic is volume charge density. Put a subtopic volume charge density. Volume charge density. The symbol is lambda sigma. Other one is lambda sigma. Other one is volume charge density symbol is rho. Rho. Lambda sigma rho. Don't you misunderstand. This rho is not normal density rho. It's rho. Don't you misunderstand it as that rho. Huh? Don't you misunderstand that story. Then same story. Then what is volume charge density? There is a volume. Write down. Definition write down. The charge per unit volume. The charge per unit volume is defined as volume charge density. The charge per unit volume is defined as volume charge density. Then rho volume. Rho volume. Okay. Right. Just think that throughout means now just consider it as a kind of a cube something. This object is kind of a cube. Now this time this charge is not spread along the surface of the sides of the cube. Actually, all charges are concentrated inside the entire volume of the cube. All the previous two cases, when it comes to linear charge density, linear charge distribution, the charge is spread along the length of the rod. When you consider area charge distribution, charge is distributed along the area, surface area of the object. But when you consider volume charge distribution, charge is what concentrated. If not, charge is fully occupied the total volume of this object. Charge is inside the entire volume of the object. Right? Okay. So let's say the same story. Same story. The total charge inside the volume. Let's say the volume is capital V. The total volume is capital V. This charge is inside the volume, entire volume. This charge is distributed throughout the volume. Then the total volume is, let's say, capital V, and the total charge inside this capital V volume is, let's say that is capital Q. Again, same logic for the capital V volume charge is Q. Then one volume, 1 meter cube volume. When you consider 1 meter cube volume, what would be the charge? That is going to be capital Q over V. This is what we defined as. Volume charge density, right? That is rho. You write down this equation. Volume charge density equals. You write down the equation. Volume charge density equals total charge over total volume. Volume charge density equals total charge over total volume. Right? Rho equals capital Q over V. Rho equals capital Q over V. Rho equals capital Q over V. Highlight the equation. You write down in words also write down volume charge density equals total charge over total volume. And highlight the story. Highlight. What is the units of a volume charge density? Then Q is measured in coulombs. Volume measured in meter cubes. Then the units of volume charge density going to be coulombs per meter cube. Right, that's it. Then we talked about what is charge distribution. Now you have a good understanding. Then we can talk about 3 types of charge distribution. One is linear charge distribution. Other one is area charge distribution. Other one is volume charge distribution. That is okay. Then we talked about linear charge density, area charge density, volume charge density. That story also very clear. Now only I'm going to teach you the most important section in this entire electric field story. Gaussian, how do we apply Gaussian theory for a given charge distribution? Now you have an idea, Nina, what is the charge distribution? You have an idea, right? You have an idea. Write and put your main topic now. Main topic now. The steps to be followed when finding, the steps to be followed when finding, the steps to be followed when finding electric field intensity at a point, electric field intensity at a point, the steps to be followed when finding electric field intensity at a point using Gaussian theorem. Using Gaussian theorem, Gauss's law, whatever. Using Gauss's law, Gaussian theorem, whatever. The topic is the steps to be followed when finding electric field intensity at a point using Gaussian theorem. Right. Now I will give you the idea. Now what's happening here? If you understood here after story, that's it. Now the star distribution stories you can understand. It's not a difficult story. Now we define electric flux. We define electric flux, and sometimes still you might have a small confusion. Effective electric flux means what? Then standard electric flux means what? You might have a small confusion there, but don't worry. That confusion will be sorted out soon. Don't worry. Okay. Right. And okay. Now, normally what they do now in the exams, normally, mainly they are asking us to find the electric field intensity. They give a point. At this point, tell me the electric field intensity. At this point, tell me the electric field intensity. Just go to the past. What have we done? And we found intensities at a point due to what type of charge distribution. Just go back to the history. When you go back to history, we found if there is a point charge. When you go to the history that we have learned up to now in electric field, if there is a point charge, due to that point charge, it can be a positive charge, it can be a negative charge, due to that point charge, at a certain point, electric field intensity is what we have found. You can remember, if the point charge is plus Q something, the electric field intensity at a point simple r distance far from this point charge is going to be 1045 silent. See the story. 1045 silent Q over r squared. So we only know this equation. Do you know other than a point charge, do you know to find the electric field intensity at a point due to a point charge? Do you know how to find the electric field intensities produced by other type of charge distributions? Do we know? We don't know, right? So far we know if there's a point charge, the intensity produced by the point charge is given by this equation. But we know that when we are learning electric field, there are many different charge distributions. Linear, area, volume, even area also there are different areas. Volumes also there are different volumes. In that cases, there are different charge distributions. When there are different charge distributions, the equation to find the electric field intensity at a point due to those charge distributions are also different, right? This equation is only for a point charge. But you can see there are many different types of charge distributions that you see. If you want to find the electric field intensity at a point due to those charge distributions, how we are going to find the intensity? With the help of Gaussian theorem. Remember, this Gaussian theorem we can use to find intensity at any point due to any charge distribution. It doesn't matter whatever the shape of the charge distribution. Whatever charge distribution doesn't matter. By using this Gaussian theorem, Gauss law, we can find the electric field intensity at any point. Do you understand? Now that is the approach. Now you know why we are going to use Gaussian theorem. Why we are going to use Gaussian theorem? Sir, the reason is we only learned to find the intensity at a point due to point charge. But sir, you told us there are different types of charge distributions. Different charge distributions create different intensities at the points. So to find the intensity produced by different charge distributions only we are using Gaussian theorem. By using Gaussian theorem, sir, we can find intensity at any point for any charge distribution. That's it. Story clear answer up now. Up now, story is very clear answer. It's very clear. Very clear. Very clear. Right, okay. Now what you do? Now what you do? Now write down. Okay, now the topic was the steps to be followed when finding electric field intensity at a point using Gaussian theorem. Number one, write down. First step. Number one, identify the charge distribution. Now we are very carefully, you must remember these steps. Huh? Number one, identify the charge distribution. Number two, this is the difficult one. First step is you can easily find it. Second step is difficult. Step number two, identify the electric field line distribution. Identify the electric field line distribution. Identify the electric field line distribution, because some students, they don't have that 3D thinking power. That's the problem. Identify the electric field line distribution. Number one is identify the charge distribution. Number two is identify the electric field line distribution. Third step. Oh, before doing the third step, inside the bracket write down. Understand symmetrical 3D nature. Close the bracket. Inside the bracket write down. Understand the symmetrical 3D nature. Close the bracket. Third step, write down. Third step. Select the Gaussian surface. Select the Gaussian surface. Some people facing a struggle in this step also. Select the third step is select the Gaussian surface. Below that step, write on a point. Below third step, write on a point. When selecting Gaussian surface, okay, you wrote me. When selecting Gaussian surface, comma, the point at which electric field intensity to be found, the point at which electric field intensity to be found must be on this surface. Highlight the entire sentence. Must be on this surface. Step number 4. Find the net charge in that Gaussian surface. Find the net charge in that Gaussian surface. The last step, write down. The last step. Use this equation. Use intensity into area, charge over permittivity. Use this equation. This one. How many steps are there? The first step is what? The first step is, first of all, decide the first step is decide the charge distribution. Whether the given charge distribution is a linear charge distribution or area charge distribution or volume charge distribution. First of all, decide that. After deciding the charge distribution is linear or area or volume charge distribution, then what you want to do is, from the charge distribution, how the way electric field lines are distributing. Second step is find the electric field line distribution. Third step is should select an area, Gaussian area, should select an area perpendicular to that electric field line distribution. When I do a question, you understand. I do now. We are discussing plenty of examples, right? First one is identify the charge distribution. Number second step is identify the electric field line distribution. Third step is select an area. We call it as Gaussian area, Gaussian surface area. Select an area perpendicular to that electric field line distribution, right? Step 1, step 2, step 3. Fourth step is we wrote as what? Step 4 is, then what we get, that is easy step. Fourth step is, inside that Gaussian surface area, find the total charge. Find total charge in that inside that Gaussian surface area. The last step is apply the equation. Charge distribution, electric line distribution, select the Gaussian surface area, total charge, find the total charge inside the Gaussian surface area, apply the equation. Now we'll discuss example 1. Example 1, around isolated point positive charge. Around isolated point positive charge. Around isolated, highlight isolated. Around, first example is around isolated point positive charge. Look at this idea. Look at what I'm doing. Here after everything you will understand. Right. We could not do past paper discussions for last 2 weeks. I will start properly. Even there is one student I will want to do it. Ne? That should be. Should do everything with my best. Then no like the satisfaction. Ne? Right. It's in the story. The story. The story is what story? Right. The story. Right. Okay. The first example is around isolated charge distribution. Around isolated is the first one. First one is isolated point positive charge. Point positive charge. Listen very carefully. Don't you think about this circle. Just think there is no such circle for now. Right now, just think no such circle. Right. Just think no such circle. Huh? Right. As they said, there is a point positive charge. See here. At the center, at here, at the center, there is a point positive charge. It's plus Q. Charge is plus Q. Plus Q. Right. It's a point charge. It's a point charge. Right. Okay. Now, what's my target? I'll tell you my target. What's my target? Now, normally what we are doing, basically what we are doing is, for a considering point, we are going to find the electric field intensity. So what is the ultimate goal of doing this entire applying Gaussian theory? What is the ultimate goal? Ultimate goal is for a interested point, I want to find the intensity. That's our target. Now, what's my target is now? I want to find the intensity at a point simple r distance far from this plus capital Q. I want to find intensity at a point simple r distance far from this capital Q. Is the point. Intensity at this point is capital E, right? The distance measured from this point charge plus Q to the point I want to find the intensity is, it's a simple law. Ratio and sum we say, do we already know the equation to find the intensity at point capital point this point answer? Do we already know the equation to find the intensity at this point answer? Do we know? Already we know that. Already we know, yes, right? Already we know. If there is a point charge, if you want to find the intensity at a point simple or far from the point charge, the equation is we know, but I am going to show how it came again. I'm going to prove again that equation using Gaussian, because this Gaussian theorem you can apply to find intensity for any charge distribution. You can apply, you can find intensity for, you can find the intensity at any point for any charge distribution using Gaussian. That's what I'm going to show. We already know the intensity equation that is going to be equal to what? 1 over 5 epsilon Q over R square. This equation we know already. This is the equation. The equation. But I'm going to show it by using the Gaussian theorem. What is the first step? First step is identify the charge distribution. Now remember, since it's a point, it is kind of a point charge distribution. But we talked about only 3 types of charge distribution. One is linear, area, volume. But this is a point charge distribution. It's a single or dot. This dot does not fall under linear or area or volume charge distribution. It's a point charge distribution. Step 1, fine. It's a point charge distribution. Step 1, fine. Step 1, it's a point charge distribution. Step 1, done. Second step is identify the electric field line distribution. Identify the electric field line distribution. Just think 3D manner. That's the point. We all know that's a positive charge. Electric field lines are leaving from positive charge in all the directions, perpendicular to that positive point charge. Then what can you say about the electric field line distribution around that point charge? This decision is the problem. Many can't decide. If there's a point, and when you draw electric field lines leaving from that positive point charge into all the directions, what type of electric field line distribution that you will get? Reply some. Reply. From the point charge, if you draw the electric field line distribution, what would be the, what shape of electric field line distribution that you will see? Any idea? If you're lying, tell me. Guys, spherical. Spherical. But I can't show that spherical, the way how electric field lines are spreading spherical. I can draw using a 2D whiteboard. So I'm drawing a circle to show the sphere. I'm drawing few lines to show spherical electric field distribution. But you want to imagine that. Hands up. Who can imagine, who really imagine that spherical electric field line distribution? Genuinely hands up. Hands up. Do you understand what I'm saying? Hands up, how many of you really understood this electric field lines are spreading in all the directions? Spherical way, hands up, spherical, all the directions. Right. If you know the electric field lines. I draw the electric field lines, I'll draw a few. Now don't forget about the circle. Because I can't draw a circle properly after I draw the diagram. That's why I drew it earlier. Don't in the circle. Right. Then we understood the charge distribution is a kind of point charge distribution. Number two, the electric field and distribution also we realized it's some kind of it's electric field and distributing in all directions perpendicular charge. That is also done. Third step is select a Gaussian surface. Select a Gaussian surface. Select a Gaussian surface. Okay, right, sir. We want to select a Gaussian surface, but remember there are two conditions. When you are selecting a Gaussian surface, remember when you are selecting a Gaussian surface, there are two conditions. Condition number one is the point where you are going to find the electric field intensity must be on that Gaussian surface. The point where you're going to find the electric field intensity must be on that Gaussian surface. The point where you're going to find the electric field intensity must be on the Gaussian surface. Point should at the Gaussian surface GS. The second point is the most important point. Yeah, both are important points. The second point is all the electric field lines passing through that Gaussian surface must be perpendicular. First point is, let's say now the point where you want to find the intensity must be on the Gaussian surface. Second point is, all the electric field lines passing through the Gaussian surface must be perpendicular to that surface, to that Gaussian surface. All the electric field lines are passing to that Gaussian surface must be perpendicular to that Gaussian surface. Then tell me, what would be the shape? What would be the shape of my Gaussian surface? Reply everyone. Then very clear. Now I have already drawn. Okay. Then I want to find the intensity at this point capital E. Then I should start drawing a Gaussian surface such a way this point A should on the Gaussian surface. And if I draw the Gaussian surface, ensuring electric field lines are perpendicular to my Gaussian surface, my Gaussian surface is going to be a imaginary sphere. My Gaussian surface is going to be a sphere. My Gaussian surface is going to be a surface of a sphere. Right? Nee? Second step is electric field lines, Gauss perpendicular. We know field lines. Perpendicular to Gaussian surface. Two conditions. Done. Right, okay. That's it. Step 1, charge distribution. Step 2, electric field line distribution we realized. Step number 3, we selected the Gaussian surface. Better I mark the Gaussian surface in red color. Then you understand here I marked in black color. Remember this is the Gaussian surface. Gaussian surface. Step number 3 also done. The radius of the Gaussian surface is going to be simple R. Okay, step 1, step 2, step 3, step 4. Step 4, find the total charge inside the Gaussian surface. What is the total charge? Inside this black color spherical area, there is only one charge, that is this plus Q. The total charge inside the Gaussian surface is plus Q. Last step, apply that equation. The last step, if you apply the equation, right? If you apply the equation, you get the same answer. See, right? The last step, okay? You follow all the steps, and if you apply the equation, or the equation they are told to apply, intensity into area must be equal to the total charge inside the Gaussian surface over the permittivity. I want to find intensity. The Gaussian surface area. What is my Gaussian surface? This black color one is my Gaussian surface. It's a sphere. It's a sphere, spherical area. We know the equation to find the spherical area is the radius simple r. So 4 pi r squared. 4 pi r squared must be equal to the total charge inside the imaginary spherical Gaussian surface is only that Q over epsilon, permittivity of the medium. When you subject intensity, same story. If you understand this idea, this story is not difficult. People tell that it's difficult, not difficult. We'll practice these past papers, and when we go to the exam, it's really nice. Then when you substitute this one, you are getting 1/5 silent. Just give over. Are scared only. Are scared only. Are scared only. That's it. Hands up. Genuinely, the story is clear. Hands up. That's it. This is the idea. Hence, the story is clear. Hands up. The story is clear. Now first one done. Likewise, we are going to find the intensities for different charge distributions. Number one done. Number two. Number two right done. Finish writing answer. Up to here. Finish writing answer. Finish writing answer. Finish writing. Finish the answer. Finish the answer. Right. Number two. Okay. Before doing the number two, shall we draw the graph also? Right on topic. The variation of electric field intensity with distance. The variation of electric field intensity with distance. The variation of electric field intensity with the distance. Right. Okay. Right. Now we are going to draw a graph how this intensity, electric field intensity, is going to vary along the distance from the point charge. Right. I erase this. I erase this. And look here. Look here. Now I'm drawing the same diagram, but I'm not drawing the full sphere. I'm going to consider how the intensity is going to vary along this horizontal line. The same manner only electric field intensity is going to vary along any line passing through point Q. Right? Look carefully. The charge is here. It's a positive charge. It's a positive charge. Plus Q. My y-axis is going to be electric field intensity. X-axis is going to be the distance measured from the charge. 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 Right. Distance, we can say simple r. Simple r. Then you understand, see this idea. Distance from the positive charge to the right side, positive distance. Distance in the left side of the charge is negative distance. But you remember, intensity is a vector. Intensity is a vector. When you're drawing the graph, be very careful. Let's define like this. Intensity is a vector. Intensity is a vector. Look here. Look here. Intensity is a vector. Now, right. Look here. Now let's consider a few points to understand the story. Family, very familiar. This point capital A. Let's take another point capital B. Point capital B and another point capital C. Right? Raise your hand, someone will say the direction of intensity. Raise your hand, someone will say the direction of intensity at point capital A is right side answer. Raise your hands. The direction of electric field intensity at point capital is right side answer. Right side, right? What is the idea? Intensity means what? When you bring +1 coulomb charge at point A, the electric flows. This is positive already. When you bring a positive charge, +1 coulomb charge at here, at point A, positive repulsive force, repulsion, at point capital repulsion. Direction of electric field intensity going to be right direction. Okay. Intensity, let's say E. Again, when you bring the intensity, direction of intensity at point capital B, point capital C, on the right side, but what happens when you go far from the positive charge? If you are going far from the positive charge, we notice that what will happen with the intensity? When you go far from the positive charge, your magnitude of the intensity is decreasing. Why? Why? When R increases, we know. I have the equation here. Can we understand? Okay. Look here, we know the equation. This equation. Intensity equals 1 over 4 pi epsilon over q over r squared. When R increases, we know magnitude of the intensity decreases. This story is clear. When R is increasing, magnitude of the intensity decreasing. This story clear. This story clear. Therefore, we know that if you represent this arrow, intensity is a bit lesser at point B. At point C, intensity is very small. Very small. Intensity A, E, B, C. Right? A, B, C. Likewise, shall we mark the intensities at point capital D, point capital E, point capital F? Point capital E. If you mark in point capital F, tell me, raise to and somebody will say, the direction of electric field intensity at point capital D is right side and up. Electric field intensity at point capital D is right side answer, right side. Left side and up. Left side. Left side. Because why? When you bring plus one column here, when you bring plus one column here, any issues connection? So we'll take a break after doing this one. After doing 1, 2, 3, some set of questions we'll do it at the break. Right. When you bring plus one column at point D, right? Positive, positive, repulsive force, direction of intensity left side. Left side. At point capital E, left side only lesser. At point capital F, intensity is very smaller. Right, okay. Now we understood that along the horizontal line from the positive charge, how would be the electric field intensity vary? Story is very clear. Now we are going to plot this graph. But remember, intensity is a vector. Normally we all know that right side direction vectors we consider as positive. Correct me? Right side direction vectors we consider as positive. Right side direction vectors we consider positive. Left side direction vectors we consider as negative. Negative. Then very clear. Right side direction. Now these are right side. These intensities are right side, and these are right side, and they are positive intensities. Right side means positive intensities. Right side means positive intensities. An issue. Hands up. Anyone facing any connection issues? Hands up. People facing connection issues. Hands up. People who are facing connection issues. Hands up. Anyone facing any connection issues? Hands up. No. Okay. No issues at all. Hands up. No issues. Everything is fine. Everything is fine. No issues. Everything is normal. No issues. Uh, no issues. If you are facing no issues, hands up. No issues, ne? Right. Okay. Then I'm explaining because my laptop is lagging. Okay, I'm doing right. If you are having an issue, please put a chat to the ACE Academy. Right. Okay. Right. Okay. Then right side direction vectors are positive, left side direction vectors are negative. Negative. Then here very clear. From the positive charge, this side, intensity is the right side direction. That means positive intensities. Right side direction intensities are positive intensities. Along the distance, what will happen with this positive intensity? They are decreasing. When you go far from the positive charge, intensity is decreasing. So therefore, when you plot the graph like this, and also when you consider this side, the left side of the positive charge, when we go far from the left side of the positive charge also, magnitude of the intensity decreasing. That's correct. When you go far from the positive left side, when you go far from the positive charge in the left side, magnitude of the intensity decreasing. Also, we know that left side direction intensities are negative intensities. Negative intensities in this column. Negative intensities in this column. Right, you are going left side. Negative intensity in this column, you are going left side. Therefore, negative intensity is decreasing. In that case, graph like this. Right? Genuinely hands up the way how I plot the graph is clear answer. Okay. I hope that you guys don't have any issues, but my lap is showing connection issues. Okay. Finish writing answer. Finish writing answer. Finished. Now only next story. Next story, number two. Number two, write down. Number two. Around positively charged, isolated, hollow conductive sphere. Next one, around a positively charged, isolated, hollow conductive sphere. Right. This story, this is important. You also draw the diagram with me, but draw the diagram with larger diagram. Don't draw smaller diagram because I'm going to draw sub-circles inside and outside. Draw large circle. Right. Follow conductive sphere. Now we'll do this and we'll take a break. We'll do this and we'll take a break. Then you understand what's happening in here. Right. Now remember, this is a hollow conductive sphere. Remember, this hollow sphere is very thin. Hollow conductive sphere. Then what is inside the hollow conductive sphere? Empty. Inside the hollow conductive sphere is empty. And when you consider the thickness of the hollow conductive sphere also very thin. Remember, the most important point, you might know the story. Under electrostatic conditions, remember, when you apply, when you insert, when you add some charges to the hollow conductive sphere, remember, all the charges will be distributed. All charges will be contaminated. All charges will be distributed on the outer surface of this conductive sphere. Remember, normally when you now, let's say now, no matter even you provide from inside to outside, whatever. Remember, normally when you apply, if not when you supply, if not when you supply, let's say capital Q amount of charges to this hollow conductive sphere, all the charges are distributed on the outer surface of the hollow conductive sphere, right? On the outer surface of the hollow conductive sphere, right? That's what remember. Okay, right. Okay, right, right. Right. Okay. Give me 1 second. Okay. If you're facing any issues, please tell me. Not if not, I'm doing explaining continuously. Right. Okay. Right. Okay. Then let's say now this is a hollow conductive sphere. Now we supplied, if not capital Q amount of charge is distributed on the outer surface of this hollow conductive sphere. Remember, normally when you supply charges, none of the charge will be inside the conductive sphere. All of them will be storing. All of them will be distributing. All of them will be contaminating on the outside of the hollow conductive sphere. That's the first story. Then if I mark the charges, they are on the outside of the hollow conductive sphere. They are on the outside of the hollow conductive sphere. Let's say you have added, you given positive charges. You have given positive charges, right? When you give the positive charge, now you have given positive charges. All these positive charges are distributed along the outer surface area of the sphere. Hollow conductive sphere. All these positive charges are distributed along the outer surface area of the sphere. Right? Okay. Raise your hands, how many we say in this, it's a hollow conductive sphere. Raise your hands, how many we say this charge distribution is linear charge distribution answer. This charge distribution is area charge distribution answer. Raise your hands, how many we say this charge distribution must be a volume charge distribution answer. Again, once again, I repeat the question. I repeat it again. Again, raise your hands. How many we say it's linear charge distribution answer? Linear. Say it's a linear charge distribution answer. Linear. Say it's area charge distribution answer. Area. So it should be volume charge distribution answer. Volume. Remember, this should be area charge distribution. That's why I told, right? I told you, right? Now, in this case, all the charges that you added to this hollow conductive sphere is storing, if not distributing, along the outer surface area of the hollow conductive sphere. Outer surface area on the hollow conductive sphere. Just take a sphere, all those q amount of charges distributed on the outer surface area of the hollow conductive sphere. Outer surface area along the outer surface of the sphere. So remember, that is a kind of area charge distribution. Do you understand? Do you understand? The first thing is identifying this charge distribution is area charge distribution. That is the first important thing, right? Okay. The total charge is then capital Q. That is a kind of area charge distribution. That is okay. That is fine. I understood. Capital Q. Right. That is the important thing. Right? Do you understand what I'm saying? How many of you understand what I'm saying? It is kind of an area charge distribution. Hands up. Do you understand what I'm saying? Because the charge is spreading on the outer surface area of the sphere. Outer surface area of the sphere. So therefore, it is kind of area charge distribution. It's not volume charge distribution. Volume charge distribution is, remember, inside, throughout this volume, all these charges are inside the entire volume of the sphere. Right? That's what I told. The difficult thing in this scenario is identifying whether charge distribution is linear or area or volume. Then identifying how would be the electric field lines distribution. Then selecting a Gaussian surface perpendicular to that electric field lines, and the point to be found must be on that Gaussian surface. That is the difficult thing. Right? Okay. Then the next, okay, first step is okay. First step is, yeah, it's a now you write down somewhere else. I'm not giving that note. You write down number one. It's a area charge distribution. It's an area charge distribution. Second step is, we know that. Second step is what? Uh, identify the electric field line distribution. I told you can remember. Under electrostatic conditions, remember, electric field lines cannot exit inside the conductor. Right? Electric field lines cannot exist inside the conductor. Okay. Therefore, if you draw the electric field lines, all the positive charges are on the outside of the conductor. When you draw the electric field lines perpendicular to the conductor, leaving from the outer surface of the conductor. Leaving from the outer surface of the conductor, if you draw the electric field lines. If I draw the electric field lines leaving from the outer surface of the conductor. Right? If you draw the electric field lines. Right? Don't you start marking the electric field lines from the center. This time, under electrostatic conditions, there can't be any electric field lines inside the conductor. All the charges are storing on the outer surface of the conductive hollow sphere. Electric field lines are leaving from the outer surface of the hollow conductive sphere. Like this. Draw the electric field lines. Electric field lines. Draw some electric field lines. You can draw some electric field lines. It's a time consuming work today we have there. Likewise, you can draw the electric field lines. Now, if you understood this one, thereafter you get the pattern, what to be done. Then you know it's not difficult. This is somewhat unfamiliar story. That's the thing. Perpendicular, also mark this perpendicular story, also mark, perpendicular, leaving perpendicular to this conductive, hollow conductive sphere. I'm not, you just mark that. I only mark on few electric field lines, mark this perpendicular story. Perpendicular story. You please mark in all the electric field lines nicely. Draw a large diagram. Right. Step one is it's a area charge distribution. Step number two is I identified the electric field line distribution also done. Step number three going to be select the Gaussian surface perpendicular to the electric field lines. Right. Now you might have problems, sir. In this case, exactly which point am I going to find the electric field intensity? So in this case, okay, now ultimate goal of doing all this thing is to find the electric field intensity, right? Exactly which point am I going to find the electric field intensity? And somebody will say, sir, we are going to find the electric field intensity inside the hollow conductive sphere answer. So we are going to find the electric field intensity inside the hollow conductive sphere answer, inside, outside answer, outside. Well, actually, we are going to find the electric field intensity from the center inside to on the surface outside. We are going to find the electric field intensity at a point inside the sphere. Then electric field intensity at a point on the surface of the sphere. Electric field intensity at a point out of the sphere. We are going to find all of them. All of them. Right. Okay. Then next story. Write down. Probably write down. Okay. You write down now. In that case, use different colors. Use that protractor, compass or whatever, and draw nice circles. If not, this diagram going to be messy. Whiteboard, I can't use only 3 colors. But when you are drawing, draw few nice colors. Right. My point capital A going to be a point inside the conductive sphere, hollow conductive sphere. Right. My point capital A going to be inside the hollow conductive sphere. So I want to find the electric field intensity at this point capital A. I want to find the equation for, if not, I want to find the electric field intensity at point capital E. Then I want to select a Gaussian surface. Perpendicular to electric field lines. But very interesting thing is, in this scenario, here there are no any electric field lines. Then how can I select a Gaussian surface perpendicular to electric field lines? One can ask like that. If there are no any electric field lines, you have a freedom to decide whatever the surface area of the whatever the shape surface, you can select as your Gaussian surface. If there is any electric field lines, you can select a Gaussian surface in whatever the shape that you prefer. But normally, what we select a spherical Gaussian surface where point A is on that spherical Gaussian surface. So I'm going to draw my Gaussian surface. You also draw it. Use different colors. Spherical Gaussian surface. See here, red color one. Point capital A is exactly on this. The point where we want to find the intensity must be on the surface of the Gaussian surface. Again and again, tell you for a reason. Okay. Right? Point capital A is point capital A. This is point capital A. This is point capital A. Right. Okay. Okay. No issues. Right. Then the distance from the center to point capital A just marked as R capital A. Just marked as R1, R2, R3 also. We can use R capital A about something also. And okay, R1 distance measured from center to point capital A going to be, let's say R1. Then at point capital A, now my target is finding the electric field intensity at point capital A. Right? Step number 1, charge distribution. It's a area charge distribution. Step number two is electric field and distribution is discussed. Step number 3, select a Gaussian surface. Now I want to find the intensity at point capital A. Gaussian surface is a kind of spherical Gaussian surface selected of radius simple R1. Right? Then Find the total charge inside this Gaussian surface. Tell me what is the total charge inside the Gaussian surface? Raise your hand, somebody will say the total charge inside the Gaussian surface is capital Q answer. The total charge inside the Gaussian surface is capital Q answer. The total charge inside the Gaussian surface is 0 answer, no charge inside the surface. 0 ni. Then sigma Q going to be 0. That's it. Apply the equation. Apply the equation, we all know that intensity into area, intensity into capital A must be going to be equal to capital Q over epsilon. So then I want to find the intensity at point capital A. Let's mark it as EA. I want to find intensity at point capital A. Let's mark it as EA. Then EA into, if you want to find the area, the Gaussian surface area going to be, you know that 4 pi radius R1 square must be equal to the total charge inside the Gaussian surface area is 0. 0. The medium, permeability of the medium is, let's say, epsilon. You know that. 0 over something means 0. Anyhow, when you simplify it, intensity at point capital A going to be 0. 0. 0. That's it. Okay, I found intensity at a point inside the hollow conductive sphere. So when you consider any point inside the hollow conductive sphere, when you consider any point inside the hollow conductive sphere, electric field intensity going to be 0. Write down. Write down. The gravitational field intensity at any point inside the hollow conductive sphere, the gravitational field intensity at any point inside the hollow conductive sphere. We'll take a break, but we'll finish this one. The gravitational field intensity at any point inside the hollow conductive sphere is 0. Is 0. Is 0. Right? Now this time I am going to consider a point, point capital B. Now I want to find the intensity at point capital B. My point capital B is actually closer to the surface of the hollow conductive sphere, but inside the hollow conductive sphere. Remember? Now I want to find the intensity at a point capital B. By point capital B is very close to the surface of the conductive sphere, but inside the conductive sphere. Again, you want to select a Gaussian. Again, select a Gaussian surface. Select a Gaussian surface. If I select a Gaussian surface inside the sphere, again nicely draw. You guys draw nicely. My point capital B is on the Gaussian surface. This Gaussian surface, right? What's my target? I want to find the electric field intensity at a point closer to the surface of the hollow conductive sphere, but inside the just inside the Gaussian, just inside the hollow conductive sphere. Let's say this is my point capital B. This is my point capital B. See this story. Here is my point capital B. So you can take this as your point capital B. Point capital B. Let's say the radius of the sphere is capital R. The radius of the sphere is capital R. Then again, I want to find the intensity at point capital B. Charge distribution is a kind of area charge distribution. Electric field line distribution is okay, same as before. Third step is draw a Gaussian surface such a way to include that point capital B also on the surface of the Gaussian surface. Yeah, it's a spherical Gaussian surface. The point I want to find the intensity is on the surface of the Gaussian surface. Done. Then find the total charge inside find total charge inside the selected Gaussian surface. That is going to be 0. Look here. At point capital B, sigma Q going to be 0. Then the last step is, fourth step is find the total charge inside the Gaussian surface. The last step going to be Last step going to be apply the equation intensity into area must be equal to Q over epsilon. Then same story 0 again 0. No need to just to show the stories only I'm doing. Then intensity at point capital B EB the area going to be 4 pi capital R square. Now the Gaussian surface area going to be 4 pi capital R square. 4 pi capital R square must be going to be total charge inside the Gaussian surface. That is going to be 0. That is going to be 0 over the permittivity is epsilon. Over epsilon. Simplified EB also 0. EB also 0. EB 0. EB 0. Now continuously we'll have some classes. I could not do last 2 weeks. I know that. But anyhow, we'll keep some classes. Now sometime this week I will skip that 26 paper class. Sometimes I will skip 27 some class and we'll focus 25 this weekend. We'll do some and we'll finish electric field. Okay, don't worry. Right, then the next one. Again, I'm going to consider I want to find, so okay, you have considered 2 points inside the sphere name. So what if shall we consider a point C? That point C is outside the sphere, but that point C is just outside the sphere. I want to find the electric field intensity at a point C that is just outside the sphere. Again, draw a Gaussian surface. This time, definitely it must be a spherical Gaussian surface because your Gaussian surface must be perpendicular to electric field lines. Then you can use different colors, but I am using only red color. Right? See, just outside. See, now we remember these positive charges are on the outer surface of the hollow conductive sphere. Right? If I select a Gaussian surface just outside the hollow conductive sphere, I just made a kind of small gap to differentiate. If you can't see any, this is just outside the hollow conductive sphere. It's just outside the hollow conductive sphere. Again, the radius is going to be same as R. This the Gaussian surface just outside the hollow conductive sphere also radius, same radius, capital R. Right, same radius, capital R. You properly mark it, capital R. The point capital C is just outside the point capital C is just outside the hollow conductive sphere. Right. This time at point capital C. This time. Resonance, how many we say? The total charge inside the Gaussian surface is 0 hands up. The total charge inside the Gaussian surface is 0 hands up. It is capital Q hands up. It's capital Q. That's the difference. Now you understand, right? Now apply same story. This is the method. Then intensity into area equals Q over epsilon. Right? Intensity into area equation. Q over epsilon. Right? Q over epsilon. Intensity at point capital C, I want to find EC. Right? I want to find EC. The area going to be the Gaussian surface area. Remember, area means Gaussian surface area. Spherical area 4 pi capital R square. Look here. 4 pi capital R square must be equal to the total charge is Q epsilon. Right? So then when you simplify, when you substitute EC going to be, right? EC going to be 1 over 4 pi epsilon C, 1 over 4 pi epsilon, capital Q over capital R squared. Capital R squared, remember? Capital R squared. There is an electric field intensity just outside. There is an electric field intensity just outside the hollow conductive sphere. So what if, okay, now understood, inside, outside. Let's consider a point which is simple R far from. So we'll consider a point which is simple R2 far from this center? Look here, the next one. Point capital D. Look here, point capital D. Uh, Point capital D, the Gaussian. Simple R2 distance far from the simple, again draw the Gaussian. Anyways, if you want to find the intensity at a point, you should draw a Gaussian surface across that point. You should draw a Gaussian surface across that point. Nice to draw circles. Right, my circles will be maybe messy. But you have devices, you can actually do the device this Gaussian surface. This Gaussian surface. Right? Mark the point as point capital D. Mark the point as point capital D. This point capital D. This is point capital D. The distance from center to point capital D going to be. You can take it as RO. Maybe you are R whatever. Simple or something. Simple or something. Now again, point capital D. Point capital D at point capital D. What is the total charge inside your Gaussian surface? Again, same as plus Q. Again, your sigma Q going to be plus Q. Then the equation, same equation. Intensity into area going to be Q over epsilon story. I want to find the intensity at point capital D. That is going to be, the area is now, the radius is R. Gaussian surface area means 4 pi R squared. 4 pi R squared. 4 pi R squared must be equal to total charge is Q over epsilon. When you substitute it, 1 over 4 pi epsilon Q over R squared going to be your intensity at point capital D. Your intensity at point capital D. Right. Genuinely hands up now. First we found for a point charge. Now we found for a hollow conductive sphere of radius capital R, when plus capital Q charge is placed on the outer surface of that hollow conductive sphere. Then charge distribution we noticed inside no intensity. So then we realized the electric field intensity values. Inside the conductor no intensity, outside the conductor intensity is how it's varying. That's what we noticed. We have an idea. Generally hands the story is clear answer. The story is clear answer. The story is clear answer. We'll take a small break also after doing the graph. There is one graph to be drawn. Then we'll take the graph. Hands up, story is clear answer. Story is clear. Story is clear. Right? Okay. Finish writing answer. Finish drawing and finding those hands up. Finished answer. Finished. Right. Now, if you finish, write the charge, write the electric field intensity variation with the distance. Write on the variation of electric field intensity with the distance. Draw the graph. The variation of electric field intensity with the distance. Draw the graph. They ask these type of things in your MCQs also. The variation of electric field intensity with the distance. Draw the graph. For this case, the variation of electric field intensity with the distance. Draw the graph. I erase this one. I erase capital D, but story you can remember me. Right. Roughly, I draw that hollow conductive sphere. Roughly, I draw here. Roughly, I draw it. Now you have the idea what's happening here. I am going to check the variation of electric field intensity with the distance along this horizontal line. Along this horizontal line, just try to understand the variation of electric field intensity. Then here, y-axis is going to be electric field intensity. right? Properly draw it. Simple R. Just try to draw that. How this electric field intensity going to vary along the distance? Just think. Just think and draw it. Same as before, but a small difference. So positive charges are concentrated on the outer surface of the hollow conductive sphere. If you draw the electric field lines, you had to draw like that only. Right. Right. Along this horizontal line, if you take few points, a point capital A, whatever. Okay, see, okay. Here, point capital A is inside the hollow conductive sphere. Point capital B also just inside the conductive sphere. Point capital C is just outside the conductive sphere. Point capital D is somewhere here. And we all know that, see what will happen. Look here. At point capital D, we realized, okay, right. What can you say about the electric field intensity at any point inside the hollow conductive sphere? Zero. Electric field intensity at any point inside the hollow conductive sphere is zero. Then here to here, electric field intensity is zero. Electric field intensity is zero. That is clear. Right. Then at point capital D, point capital E, point capital F, what is the direction of electric field intensity at point capital D? Your electric field lines are going right side direction, right? If you mark the electric field intensity direction at point capital D, that is going to be right side, right? And when you go for same story, the equation, remember, look here, remember, electric field intensity at point capital D, you wrote that. Electric field intensity at point capital D, you wrote that what equation? You wrote that ED as what? 1 over 4 pi epsilon. It's 1 over 4 pi epsilon Q over R squared. R means what? Distance measured from center to the point capital D. When the point capital is somewhere here, somewhere here, somewhere here, what will happen to the R? R is increasing. R increases. What will happen for your electric field intensity? Decreases. Then we understand that when you go far from the hollow conductive sphere, your electric field intensity decreasing. Your electric field intensity decreasing. That story you guys understand. Electric field intensity decreasing. Right? In this story the same. Right? When you go far from the hollow conductive sphere, your electric field intensity is decreasing. Right? Decreasing. Electric field intensity decreasing. And seems to the right side direction positive vector, left side negative vector. Intensity is a vector, right side direction positive, left side is negative, right side is positive. If you draw the graph, right side is positive intensity. That is above this horizontal axis. This is the right side. These values are positive intensities. Right side intensity is positive. When you go far from the holoconductive sphere, intensity is decreasing. Likewise, when you go to the left side, when you go to the left side also, when you go far from the holoconductive sphere, when you go far from the holoconductive sphere, then also electric field intensity decreasing, but left side intensity is negative. Left side intensity is negative, therefore, like the previous graph only, like this, right? This like this, like this. What we can do here, we can touch this. Here we can touch this axis. Here, this graph does not touch the horizontal axis, but this graph is touching this vertical axis. Touching. So some people do they like this. Some people what you do, they just draw, they connect like this. No need. No need to do like that. No need. Genuinely hands up, stories clear hands up. Genuinely. Everything is crystal clear hands up. Everything is crystal clear hands up. The way how I drew the electric field inside the graph is very clear hands up. Very good. Time to take a break. Very clear hands up. Just very clear hands up. It's very clear hands up. It's very clear. Right. Now this week I will definitely do many extra classes and want to finish this story in the electric field and want to finish this. Right. Okay. How long will take a break? Time is almost 10:40. I think start at 8 o'clock. I think first time I'm doing a class continuously for more than 2 hours and 40 minutes. Without giving a break, right? We'll take a small break. How long you want? Just tell me someone how long you guys want the break. What to do? The next one is next. How long you want to do? Now that's it. The next one, likewise, we have to do many. So the next one is isolated charged non-conductive solid sphere. After doing this, this one, the remaining are not that much serious. Then again we have to learn. Again we have to learn again that then capacitors. Okay, we can finish. If I do 2 or 3 classes, electric field, I can finish it. Then I will give priority to TUT questions, past paper questions in electric field. Right? Electricity and magnetic field, I can parallelly I can do. If I can put these questions in the papers also, then that's it. That's it. Right. Okay, how long you guys want the break? Just tell me, guys. How long you guys want the break? How long will it take? Tell me quickly. Tell me quickly how long will it take the break? 15. 15 minutes. Okay, we'll take time 10:42. Come at 10:55 something. 10:55 again. We'll do until 12 o'clock. Might do. Okay, take a break and come. Yes, right. Number three. Next one, write down. Number three, write down. Around isolated, around isolated, comma charged, comma non-conductive, non-conductive, isolated, charged, non-conductive, solid sphere, solid sphere. Please highlight those things. Isolated one color, uh, obviously charged ni. Then non-conductive one color, solid sphere one color, one color. Non-conductive solid sphere. Right. This story, this story, this story. Right. Now, look here. Right. Write down below that point. Write down here the total charge distribution. Here the total charge distribution. Here the total charge distribution in this non-conductive solid sphere is capital Q. In this non-conductive solid sphere is plus capital Q. Plus capital Q. Right. In this story, this time. Look here. Now this is non-conductive. I told you under electrostatic conditions, if it is a conductive sphere, there aren't any charges inside the conductive sphere. But if it is non-conductive, remember, there can be charges inside the non-conductive objects. There can be charges inside the non-conductive objects. Now this is some kind of non-conductive solid sphere. Non-conductive solid sphere. In that case, how are we going to do the story? Right. If I do the diagram, look here. Right. Just think and give me 1 minute. I'll be back. Yes, okay. Yes, right. Non-conductive, solid conductive sphere. Solid conductive sphere. Not hollow conductive sphere. This is conductive hollow. Conductive hollow sphere. Now I'm going to draw the non-conductive solid sphere. Right. If I draw that story, better you draw larger diagram. Okay, don't draw a diagram like me. Draw larger diagram. Draw larger diagram. The solid. Non-conductive solid sphere. Then I told you that if it is an unconductive object, when you supply capital Q amount of charge to this object, remember all the charges stored throughout the non-conductive solid sphere. My first question is, raise your hand someone if you say the charge distribution going to be a linear charge distribution answer. It's linear charge distribution answer. Linear. It should be area charge distribution and sum. Area. So when we insert capital Q amount of charge to this non-conductive solid sphere, the charge is going to distribute as an area charge distribution and sum. Area. So it should be a volume charge distribution. It's going to be volume charge distribution. Why? Because all charge is going to what? Concentrate throughout the volume of that non-conductive solid sphere. Okay, right. Okay. If I do them positive charges, center is here, positive charges. Right? It's a volume charge distribution. Now I think you understand the story, right? So what you do again, take a point inside on the surface outside and find intensity is at point A, point B, point C. Now you can do it. Now you can do it. Center is here. Center is here. But remember, there are nice stories here. Nice stories. They're not unlike this is somewhat easy. But when you're doing the calculation, there are some tricky stories also there. Center is here. The radius of this non-conductive solid sphere, I mark the radius as capital R also. Radius capital R. Right. So now I want to find the intensity at a point inside the sphere. How can I do that, sir? You do it now. You know the story. You know how to do that. You know the story. Just do it. Just do it quickly. Just do it quickly. Just do it quickly. Right. Do it, do it, do it. Do it quickly. Do it quickly. Do it quickly. Right. Now then my Gaussian surface. So I'll consider a point capital E inside this non-conductive solid sphere. My point capital is somewhere here. Then as you told that, sir, I want to create a Gaussian surface. I select my Gaussian surface as Select. You guys know what to do now. Select your Gaussian surface. My Gaussian surface is going to be, sir. My Gaussian surface is going to be, sir. So my Gaussian surface is going to be, this is what my Gaussian surface. This is my Gaussian surface. Right? Gaussian surface. You can name Gaussian surface A dash O. You can give a name. Right. My point capital is somewhere here. It is my point capital E. Let's say the radius of the Gaussian surface from the center is, let's say, capital R. Simple R1. The radius simple R1. Okay, I hope you guys can see what I'm doing. Then shall we find the intensity at point capital E? Then we can say that you might face a very big problem. Intensity at point capital E, the total charge that you supplied for non-conductive solid sphere of radius capital R is plus capital Q. You supplied plus capital Q charge. You supplied plus capital Q charge. Right. Now, okay. Now, first step is if you want to find the intensity at point capital A, first step is identify the charge distribution. It's a volume charge distribution. Number two, second step is draw the electric field lines. Draw the electric field lines. Electric field line distribution. Number two is electric field line distribution. Remember, in here, electric field lines, when you consider a conductive hollow sphere, we didn't see any electric field lines inside the conductive sphere. But remember, when it comes to the non-conductive solid sphere, when you draw the electric field lines, remember, electric field lines are starting from all directions, everywhere, like this. And this diagram might be a bit messy. You guys nicely draw it, huh? Electric field lines. Just draw it, electric field lines. You draw electric field lines everywhere. Shall I zoom in? Hands up who want to zoom this diagram, hands up. Hands up who want to zoom. Right. Or they can ask, see the way how electric field lines that we drove for this scenario. The way that we are drawing the electric field lines of this scenario. See, next problem is okay. Number one is charge distribution is it's a volume charge distribution. Number two is the electric field line distribution is okay. Select a Gaussian surface perpendicular to the electric field lines, and point A must be on the Gaussian surface. Spherical Gaussian surface selected. Spherical Gaussian surface of radius simple R1 is selected. Okay. Fourth step. My question. Raise your hands. How would we say? Delta Q is capital Q answer. Raise your hands. How would we say? Delta Q is capital Q answer. Raise your hands. How would we say? Delta Q is capital Q answer. Sir, delta Q is not capital Q, sir. Answer. Delta Q is not capital Q answer. So delta Q is not capital Q, sir. So delta Q is not capital Q. Remember that capital Q charge, for an example, 500 coulombs of charge. That 500 coulombs of charge, that capital Q charge has given to this entire non-conductive solid sphere. Throughout this entire volume of the non-conductive sphere, the total charge is capital Q. But currently what I want to find the total charge only inside the Gaussian surface. I need this Gaussian surface as A dash. Gaussian surface A dash. You write down. Gaussian surface A dash something. A dash Gaussian surface. What's my target? I want to find the total charge inside the Gaussian surface A dash. Is that exactly capital Q? No, right? Because capital Q is the total charge on the entire volume of the non-conductive sphere. Then, so how can I find? How can I find then? Then you can tell that story. Volume. Then you can find that volume density story. Volume charge density. Sir, that means you are telling, sir, we inserted capital Q amount of charge for the entire volume of the non-conductive solid sphere. The volume, the radius of the non-conductive solid sphere is capital R. Then I can find the volume of this non-conductive solid sphere. The volume going to be, we know sphere volume, spherical volume 4 over 3 pi capital R Q. For this entire volume, the charge that you have given is capital Q, sir. Then, very simple. For the entire volume of the non-conductive sphere, the charge given is capital Q. If I want to find the charge inside the Gaussian surface, then you want to find the volume inside the Gaussian surface. Radius of the Gaussian sphere is R1. What is the volume inside the Gaussian surface? 4 over 3 pi R1 square. Learn these stories. 4 over 3 pi R1 square. That charge, let's say the charge, let's say Q1 no something Q1 no Q dash or QA or whatever. And now you can find the answer. Now you can find this Q1. Now you can find Q1. Now you can divide Q1 over Q, right? Then 4, 3, 4, 3, pi, cancel out. You can write down Q1 over Q must be equal to Q1 over Q must be equal to what? Must be equal to 4, 3, pi, cancel out R1 cube over capital R cube. When you substitute Q1, you can write down R1 cube over capital R cube dot capital Q is Q1. Generally, hands up. I found the total charge inside the Gaussian surface. That is R1 cube over R3 cube dot Q. This story is clear, hands up. How the way I found the total charge inside the Gaussian surface. This story is clear, hands up. This story is clear. This story is clear, ne? This story is clear. Then easy. Then my delta Q going to be fourth step. Fourth step delta Q, ne? Fourth step is my delta Q. Fourth step is delta Q. Then we know at point capital A. At point capital A, we know that delta Q going to be I found delta U is how much? R1, that is Q1. That means R1 cube over capital R cube dot capital Q. Then the last step is apply the equation, sir. If we apply the equation, we know that's the intensity into area going to be equal to capital Q over epsilon. So then intensity at point capital A going to be, sir. Intensity at point capital A going to be, sir. The Gaussian surface area, the radius R1, Gaussian surface area, we know that. See, look here. 4 pi R1 squared. The charge going to be, sir? The charge going to be Q I found, that is R1 cube. See, sir, R1 cube over capital R cube, that is capital Q. Over epsilon, sir. Epsilon. So when you see here R1 squared and R1 cube, the remaining is R1. So when I substitute capital E intensity at point capital A, see, nice, right? Now same story. Now you understand how to find the Gaussian, how to apply Gaussian, and you know how to find the stories. When you substitute it, you are getting, see, 1 over 4 pi epsilon, right? 1 over 4 pi epsilon. See what I am doing. 1 over 4 pi epsilon. 1 over 4 pi epsilon, right? 1 over 4 pi epsilon. 4 pi epsilon is there. Q R squared dot R1. Q R squared dot R1. Is it correct? Am I correct? Just check. You guys cross check. The equation I wrote is right or wrong? You guys cross check the equation I wrote right or wrong. Right, the equation I wrote is right or wrong. You guys just cross check. If you guys just cross check it. Cross check, right? Cross check. Then here 1 R1. Here it's Q. R cube. It's R cube. R cube. Hands up to everything is very clear. Hands up. Hands up to everything is very clear. Hands up. Very clear. Hands up. If you understand, hands up. R cube over here, what I wrote here, epsilon. Story. Okay. Right. Okay. Right. Now you understand. So that means, sir, now only understood the story. Sir, we wanted to find the electric field intensity at a point inside this non-conductive solid sphere, right? Since it's a volume charge distribution, so based on the Gaussian surface that you select inside the sphere, the charge inside the Gaussian surface is going to be changed, right? That story we have described how to find, in that case, how to find the total charge using the volumes and all you explained here. I got an idea. Then you applied the steps and you found the electric field intensity at a point inside the non-conductive solid sphere, 1 over 5 epsilon Q R cube R1 something. So in this equation, 1 is nice. 1 over 5 epsilon is a constant. The Q means the charge that we given is a constant. Radius of the non-conductive space is a constant. That means when the distance R1 means what? R1 means distance to point A from the center. When R1 increases, when your point A is somewhere here, right inside the sphere, when you are R1 inside the sphere, when your point A is going far from the center, when R1 increases, intensity at that point also increases, right? Then I understood, sir, only variable is R1. When R1 increases, right, R1 means, remember, I am talking about inside the story. When the point is inside the sphere, the intensity. When R1 increases, your intensity also, remember, increases. A story, remember, also there is a kind of direct relationship between, remember, there's a kind of direct relationship between intensity inside the point, intensity at any point inside the sphere, right? Direct relationship between intensity inside the sphere and the radius. Okay, that is clear. Right, the story is clear. We wrote up to here. Let's consider now, sir. Okay, right now I want to find the intensity at a point, sir. Now I want to find the intensity at a point just outside the sphere. If not, you can take just inside the sphere also. You can take just outside the sphere. If not, you can find just inside the sphere. Same story. Same story. Let's consider just outside the sphere. Again, draw a Gaussian surface. If you draw a Gaussian surface just outside the sphere. Now we want to understand why we are always drawing, sir. So why so far all the Gaussian surface are spherical, sir? Why? Because we know that the requirement is your Gaussian surface must be perpendicular to the Gaussian surface must be perpendicular to the electric field lines. To satisfy that, we had to draw currently. So far we have drawn what? Spherical Gaussian surfaces. Your point capital B. Your point capital B is somewhere here. Point capital B. The distance to point capital B from the center is radius capital R. Capital R ne? Capital R. Now at capital B will find the at capital B will find the sigma q. Raise when somebody will say, sir, when you consider Gaussian surface just outside the non-conductive solid sphere, the total charge is going to be same as plus q and so. The total charge is going to be same as plus q and so. If the Gaussian surface is just outside the non-conductive solid sphere, the total charge inside that Gaussian surface is going to be plus capital Q and so. Plus capital Q and so. It's not plus capital Q and so. It's not plus capital Q and so. 11:30. Oh. Now simple now. Why? What's the wrong? What's the problem? Now very simple story. Ne? First of all, what you do? I'm asking. Now your Gaussian surface is this one. Ne? Just look at the Gaussian surface. Now you want to find the intensity at point capital B. You drew a Gaussian surface across point capital B. It's a spherical Gaussian surface. Your entire non-conductive sphere is inside that Gaussian surface. Then I'm asking, what is the total charge inside the Gaussian surface? Hands up, it is plus capital Q hands up. Sir, it's not plus capital Q hands up. It's not plus capital Q hands up. It's plus capital Q neither. When you consider now if the entire sphere is inside the red color Gaussian surface B, don't you agree that total charge is plus capital Q? Hands up or don't understand hands up? I don't know, please respond. Please respond, please. Very difficult to do a session like this. If you don't understand, hands up. Don't understand. Now you know that. Now how to find the charge? Very simple. Look here. There are toffees. Hands up, how many we say? There are 4 toffees inside the sphere. Hands up. This is the sphere. How many? There are 4 toffees inside the sphere. Hands up. So there are only 2 toffees. Hands up. So there are only 2 toffees. That is simple. Ne? Simple meaning. Remember always. Now what's your target? Your target is to find the intensity at point capital B. Where is point capital B? Point capital B is just outside the conductive sphere. Where is point capital B? Point capital B is just outside the conductive sphere. Look here. This is your conductive sphere. The total charge inside the conductive sphere is plus capital Q. Where is your point capital B? Point capital B is just outside the conductive sphere. You have drawn a Gaussian sphere. You have drawn a Gaussian surface. Just outside the conductive sphere, you have drawn a Gaussian surface. Just outside the conductive sphere. This red color one is your Gaussian surface. Gaussian surface. My question is, what is the total charge inside the Gaussian surface? And suppose is the total charge inside the Gaussian surface plus capital Q answer. It's plus capital Q, right? That's what I'm doing. I selected the Gaussian surface that is just outside the sphere. Then your entire sphere is inside that red color Gaussian surface. If the entire sphere is inside the Gaussian surface, total charge inside the Gaussian surface is same as the plus capital Q. Hence the story genuinely clear answer. Genuinely clear answer. Genuinely clear. Genuinely clear. That's it. That's it. That's it. Plus capital Q. Apply the equation. Apply the equation. Intensity into area must be equal to Q of epsilon. Then intensity at point capital C. Sorry, capital B. Intensity at point capital B must be into area. Area means Gaussian surface area. The radius of the Gaussian surface is capital R. You nicely draw a different problem. 4 pi capital R square, the area of the Gaussian surface 4 pi capital R square. The total charge inside the Gaussian surface, that is capital Q, epsilon. In subject capital EB. You subject EB, you get the answer. You subject EB, your EB going to be how much? Your EB going to be, see, your EB going to be, look at here, 1 over 4 pi epsilon capital Q over R square. Story. Right. Clear? 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 Then we found a point inside. We found a point just outside. Shall we find a point a bit far from the outside? Shall we find the intensity point a bit far from the sphere? Point capital C. Somewhere here. Point capital C somewhere here. Draw the Gaussian surface. If you draw a Gaussian surface, point capital C. A point capital C, draw Gaussian surface. If better you use different colors, then you can understand more. Gaussian surface. Here is your point capital C. Here is your point capital C. This is your point capital C. Let's say the distance, see, the distance to point capital C for the center is, let's mark it as, let's mark the distance to point capital C to center is, let's mark it as simple R2. 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 Since this diagram is not clear, for you to understand the diagram, I draw this diagram, then you will understand. Since the diagram is not clear, only I am drawing this diagram. Look here. This is your Gaussian surface passing through point C. This is your Gaussian surface passing through point C. Right? And the non-conductive solid sphere going to be inside. Going to be inside. Right? The total charge inside the non-conductive sphere is plus Q. Plus Q. Where is point C? Here is your point C. It is your point C. The distance from the center to point C is going to be what? R2. R2 ne? R2. Gaussian surface. Ratio and sum to see the total charge inside the Gaussian surface passing through point C. The total charge inside the Gaussian surface passing through point C is same as plus capital Q and sum. Is same as plus capital Q and sum. Same as plus capital Q. Understand, right? Now you know inside different, outside same. Then apply the story. Apply at point C. But see here at point C. At point C here, the total charge going to be sigma Q going to be how much? Same as plus capital Q. Now you know this is what we are going to do for few more examples, and we are finishing Gaussian, right? Gaussian. Now tomorrow morning I will do that paper session and we'll cover it. Tomorrow morning, tomorrow evening can't do a class. Tuesday we'll do a class. Tuesday evening we'll do a class, and Wednesday, Tuesday we'll do two sessions. Possibly we'll do it. Tomorrow we'll do night. Not tomorrow, Tuesday. And Wednesday I might cancel the possible discussion for 26 theory people, and I take that time and I will do a class on Wednesday also. Thursday also we'll do it. Somehow if you finish electric field and electricity, then magnetic field is a small section, right? We'll see. We try, need your support, and you want to support me, then only we can do nicely. If not difficult, right? Intensity into area, because we are writing papers, paper writing, everything is there. Keyword is silent. Only last 2 weeks only we could not do everything properly, but up to now revision classes and all, everything went so nicely only. Right, we'll do until the last day. Okay. Then intensity point capital C AC. What is your AC? Your AC, the area means Gaussian area, Gaussian surface area, spherical Gaussian surface. The radius R2, 4 pi. The radius R2 square. Total charge is Q. Epsilon. Look here. If you subject EC, your EC going to be 1 over 4 5 silent, 1 over 4 5 epsilon Q over, look here, R2 square. See here. So in this case, sir, in here, sir, look here, sir. Sir, 1 over epsilon is a constant, Q is a constant. When the point C is far from this non-conductive solid sphere, when the point C is here, when the point C is moving far from the non-conductive sphere, here, what will happen for your intensity? What will happen for your intensity? So when R2, when the point C is going far means R2 is increasing. So when R2 is increasing, your intensity going to be decreasing. But there is no any linear relationship. Intensity is inversely proportional to 1 over R square. See, here you can get the idea. Here in a curvy graph, intensity is proportional to 1 over R square. A curvy graph. That's it. We'll do the graph, then and we'll finish for now. Right. Shall I do the graph? Okay, genuinely hands up. Up to now, everything is very clear, hands up. Up to now, everything is very clear, hands up. Very clear answer. Very clear. Shall we do the graph? We'll do the graph. Intensity, we'll do the intensity distance graph. Just draw it. Intensity distance graph. Just draw it. Just draw it. Just draw it. If you draw that. How can I do this? How can I do this one? This one. Now again, draw a sphere. In this case, right? How do you draw the graph? Almost same graph, small deviations. Intensity, distance. Look here, what's happening here? Look here. I told you the insight. When you consider, if you mark the intensity, if you mark the intensity, right? Remember, intensity going to be right side, right side. But when you notice, when you consider insight, what's happening with the radius? Yeah, I explained here. See, inside the non-conductive solid sphere, intensity is proportional to the radius r. Right? When the distance from the center, when the distance increases, from the center, the distance increases, your intensity also increases. The relationship between intensity and distance is a kind of linear relationship. Kind of linear relationship. You have to remember. You have to remember. Kind of linear relationship. Got it? Why? Inside the sphere, from the center to the radius, intensity proportional to the radius, intensity proportional to the radius is the distance. Right? The reason you know. The reason is intensity proportional to the distance. Right? Thereafter, same story. Thereafter, when you consider a point, outside the sphere, and when that point is going far from that sphere, this story. Intensity is inversely proportional to the distance. Distance increases means intensity decreasing curvy manner. Right? This story I explained, okay? I explained why it's getting like this. Intensity decreasing. Intensity decreasing. Right side intensity. R positive intensity. Here, same story. Left side intensities. If you mark the, look here. If I mark the intensity here, intensity is increasing. Just, I don't know whether you can see the arrows. Let's see, I try to zoom in. Arrows. Now inside the sphere, from the center to the radius here, intensity increasing left side. As it passes the sphere, from outside to the infinity, outside to away, again intensity is decreasing, intensity decreasing. And this is the largest arrow belongs to be here, then decreasing. Nice story, ne? Nice story. Nice story. I think we gave a good start. I think we gave a good start for this indigenous stories. I think I gave a good start. Okay, time is almost 10:40. Hands up, everything we learned today. Today, I think we have done more than 3 hours. Everything is very clear, answer. Everything is very clear, answer. Very clear. Very clear. Don't worry, somehow today is today it's 27. Now 29 will do a class, 30 will do a class, 31 will do a class, and somehow we'll go to the capacitor last section in electric field. Right, parallelly we'll do that past paper story. So don't worry now. We'll do. Anyhow, next week we'll start electricity and we'll start magnetic field and we'll go to that part. What? Viscosity and elasticity, some past paper questions. We'll do it. Right? Okay. Then study well and if you have any issues, please tell me. Right, tomorrow we might have a class early in the morning, 7 a.m. to complete that pending questions. Right? Okay. So then we'll stop the class for today and right, study well. Huh?